In this video, we'll just reintroduce you to the concept of the mole and what you need to know. So the mole is a measurement of quantity. It's just a word which means a certain number. So instead of having to say the same number all the time, we give it a name, and that name is the mole. We have a similar concept in English with a couple of words. The common one is a dozen. If I say a dozen, I mean 12. A dozen eggs is 12 eggs. A less common one, but one you might encounter, it's used in Lord of the Rings at Bilbo's party once, is a gross, which is 144. So a mole is just a number which mole is just a word which translates to a number. But the number in question is a very large number. By definition, since 2018, it used to have a different definition to do with carbon, which was a definition based on measuring it, and actually left open the possibility that future measurements might change the number slightly. But scientists have decided that we're now at a state where we actually can say to a good enough degree of precision, to, let me count them, 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures, what the value of the mole is. And it is 6.02214076 times 10 to the power of 23. Things. Doesn't have a unit because it's just a number. So, numbers don't have units, they're just numbers. It's a very, 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 very big number. It's a very, very big number because it was chosen to represent a relationship between the number of particles or molecules or bits of substance at a very small level in quite big level things, things that chemists use, quantities that they can deal with in grams or kilograms. That number is, by the way, also known as Avogadro's number. Okay, so Avogadro's number and the mole are kind of the same thing, really. Why you need two different names for it, I've never been quite sure, but it means the same thing. The concept of molar mass, well, the whole idea here is that for any given thing, the mass of one mole, the mass of 6.02 approximately times 10 to 23 of that thing, is the molar mass as measured in grams or kilograms. So potentially you could have a molar mass for elephants, which would be lots and lots and lots of kilograms. Okay, but for atoms, and molecules and things on this scale, then Avogadro's number, the reason why that particular number is a mole, is so that the relative atomic mass in the periodic table, or if you add them together, the masses in a molecule or an ion or a few atoms stuck together or whatever, that atomic mass or relative mass equals the molar mass in grams. So the mass in atomic mass units, if you have a mole of that thing, if you know the mass in units of U, atomic mass units, and then you know that the mass of an Avogadro's number of a mole of that thing is the same number but in units of grams. For example, carbon, if you have a bag of carbon with a mixture of carbon 12, carbon 13, carbon 14, on average it'll have a mass, atomic mass units of 12.011 per atom on average. So we can say that the molar mass of carbon is the same number, 12.011 grams for every mole of carbon that we have. And the same applies to anything else. So other elements on the periodic table, you can look them up on any decent periodic table, will have these values. So for hydrogen is normally just one proton and one electron, but you do get isotopes called deuterium, which has 2 protons, and even tritium, which has 3 protons. and therefore on average the molar mass of hydrogen is a little bit more than 1. It's 1.008 grams per mole. So if you have a mole of carbon atoms and you have a mole of hydrogen atoms, you have the same number of both, but because carbon atoms are about 12 times heavier, a mole of them will weigh about 12 times heavier. Oxygen is heavier still. Oxygen has an atomic number of 8, but its mass on average is 15.999. Most oxygen atoms, a vast majority of oxygen atoms are 16, 8 protons and 8 neutrons. But there are some isotopes with different numbers of neutrons, either more or less, and the average is 15.999. So you can say that the molar mass of oxygen atoms is 15.999, and if you've got a compound involving oxygen, then that's the number you'd use per oxygen atom. But it is all worthwhile remembering that, again, if you're dealing with oxygen as a gas, the oxygen you have in the room that you're sitting in, it won't go around as just oxygen. It always forms the diatomic molecule O2. Okay, the Lewis diagram for that is shown there. It's got a little double bond on it, and that is O2. So the molar mass of oxygen atoms is actually 29.998 grams per mole, because if you have 1 mole of oxygen atoms, then you actually, 1 mole of oxygen molecules, then you actually have 2 moles of oxygen atoms, because there's 2 atoms per molecule. And for more complicated formulae, then you follow the same method. If you want to know the mass of water, you wouldn't say atomic mass at this point because it's not an atom. It's 3 atoms joined together in a compound. So the most generic way of referring to this is formula mass, because then any chemical formula you can write down, you can talk about its formula mass. So the formula mass of water, if I have a mole of water molecules, that's 18.015 grams per mole, made up from 2 moles of hydrogen at 1.008 plus 1 mole of oxygen at 15.999. Add it all together, you get 18.015. So let's try a little more complicated compound. Glucose, a sugar found in plants and animals, and it has the formula C6H12O6. So by combining the atomic masses of the constituent elements, constituent atoms, what would the formula mass of glucose be? Carbon is 12.011, you got 6 of them. Hydrogen is 1.008, you got 12 of them. And oxygen is 15.999, you've got 6 of them. If you need to, pause the video, have a go at this. And the answer is 180.156 grams per mole. So if you have a mole, 6.02 times 10 to the 23 molecules of glucose, you'll have 180 and a bit grams of glucose. Yeah, small bag of sugar, really. Sachet of sugar. Okay, so how do we actually use this? That's the basis of chemistry and chemical reactions, and that's what we'll look at in the next video.